this work was supported by two grants, so I'm going to put that up. The first is an NIH grant that we had and a National Science Foundation grant. And I can talk to you at length about those if you ever want to hear about those. But we thank these people for the money, particularly the NIH. It was a significant amount of money. So let me give you some history. We began changing our laboratories in 2008. And what we tried to do was introduce physics education research in foreign materials, and we did it by going into the labs and the recitations. And partly that was done because the faculty were not in total agreement, and a lot of them didn't want this, and some of them it's because they don't really know what it is, or they think it will take a lot of time and a lot of issues. So we didn't have total agreement from faculty, and we went in and did it anyway. And so I'm going to tell you what we did. We did it in the labs and the recitations, and we had some resistance, is the truth of the matter. So I'll put that out there, but it matters when there's resistance in the department. It makes a difference. So the faculty were not unified. They weren't in agreement in this implementation. So what we did was they continued to teach however they taught in the lecture, and most of them taught traditionally. Okay? However, we had a number of faculty who teach non-traditionally, who use interactive engagement, who use research-based materials, and so those faculty interacted a whole lot more with the labs and the recitations and with the TAs and people running the labs. And so we have a nice comparison actually of traditional lecture and non-traditional lecture with these research-based labs and recitations, and also labs and recitations taught traditionally. We have some of that data too. So we started this in spring 2008. In fall 2008, we started up in the algebra-based courses, and we added recitation sections. We had not had recitation sections in physics, at least not in recent history at this point in time. So recitation sections were new, and we added an hour recitation each week. And at first, we stuck it onto the lab. So you had 2 hours of lab and 1 hour recitation in a 3-hour period. So that's what we did. And most of that was a scheduling problem. And then we started it up in 2009 in the calculus-based classes, the same kind of thing. In the calculus-based classes, it started that way with 2 hours lab, 1 hour recitation, and it's now been separated out. So you have 1 hour recitation and 2 hours lab at different times when you leave. So it's a little bit different. In fall 2009, we got this large NIH grant, and we had then an opportunity to assess what was going on. So the NIH grant was for assessment, and they wanted assessments that existed. Well, the only kind of things that exist in physics are things like FCI, MBT, BEMA, if you know what those initials are, and I think this group mostly does, Force Concept Inventory, Brief Electricity and Magnetism Survey, Mechanics Baseline Test is MBT, and there are a couple others out there. So we decided to use those, and then we also decided to do a few others. This is what I just said. There are a few valid and reliable assessments. So for valid and reliable assessments, we chose the existing ones like Force Concept Inventory. But then we decided we'd also do free response pre and post tests. It's a different kind of assessment, and we also wanted that data. The conceptual inventories are all multiple choice. That may make a difference. You don't have to explain your reasoning. Your thinking skills may or may not show up in your choice, and we had to think about those things. So we ran 2 different kinds of assessments. We also had assessments on TAs, like how well they were teaching and things like that. We had that going on simultaneously. Okay, so basically we had the Force Concept Inventory, Mechanics Baseline Test, Brief Electricity and Magnetism, Survey of Electricity and Magnetism. Those were the 4 we basically chose, and the free response. And the other ones were the Colorado Learning Attitudes about Science Survey, Loss and Test of Scientific Reasoning, and Reform Teaching Observation Protocol, and I'm not going to talk about the 3rd bullet in this talk. Okay? So first the FCI and BEMA, but let's do a little bit of general information about our courses. The algebra-based students are predominantly health science majors. They are traditionally, they've been taught in a lecture format. And then we started adding these 1-hour recitation onto the 2-hour labs. And these went in by first using real-time physics, which is a research-based lab, and we put those in the algebra-based course. And in the second semester, we took some of the real-time physics labs, and then we wrote some of our own, because real-time physics at that time only covered circuits and a few other things and didn't cover the whole course. And so we wrote our own. By fall 2010, they're almost all locally written. So we wrote our own research-based labs. Okay, so we have a whole set of locally written research-based labs. Students don't do a formal write-up with these labs, but they do weekly homework, and they have bi-weekly quizzes that were in the recitations. And the labs and recitations are common among all instructors, okay? So your lab and your recitation are you could have anyone from any instructor in there. It's all mixed. Okay. We also have a course which is an inquiry-based laboratory course, which we developed with NSF money around 2001, and it's been taught since then, about 14 years. It's no lecture, no text, completely hands-on, laboratory-based. It was designed specifically for people in the health sciences. We tried to take their needs and backgrounds into account, and it's run a completely different way. We started redoing workshop physics for that course, but ended up basically writing our own course, drawing on workshop physics and a couple other things that were already out there. So we also have data on that course, which I'll tell you about. So it's been taught, I guess, 14 years now. Like I said, there's no lecture, no text. The materials are on the computers in the lab. You do experiments first, and then from your observations, you develop the theories, you develop the equations, and you generate what's in most textbooks, and then you use those equations and theories to solve problems. So you do the experiments first, and the attempt is to learn as if it's never been done before and make it exciting. On the other hand, it's directed inquiry, it's guided inquiry, so that it's not brand new, like you have to reinvent the wheel for yourself. Okay, so, and that's all on the web somewhere if you want to look at that. I can give you links to that. Our calculus-based course is mostly, primarily engineering and computer science majors. There are a few other majors that feed into there. They also started a recitation in spring 2009, in addition to the 2-hour lab. The introduction in here, it was this is where most of our resistance was in the calculus-based course. And it was done actually in a way that it blocked what we were actually able to put into the labs. And so it was kind of put in piecemeal. We have a time when they had some real-time physics labs and some traditional labs. Then we did one semester with real-time physics labs, and then we used some from the University of Illinois, which are also research-based labs. So that was a big mixture, and a lot of controversy over what we were allowed to do in that. Again, the labs and recitations are common among the instructors. Most of the faculty taught in traditional lecture style. They primarily focused on the lecture and left the labs and recitations to the TAs and whoever was coordinating the labs at the time. And as this progressed, we actually had a lab coordinator. We didn't have that even at the beginning, but then we had a lab coordinator. Very few of them use PER-informed pedagogy or interactive engagement techniques, but some instructors do, and they were the ones who were more likely to work with the TAs and lab coordinators. And work on the pedagogy to be used in the recitations. So we tried to put the PER-informed pedagogy and materials in the recitations and the labs, and left it up to instructors if they wanted to work with us or not. So the TAs were trained in lab and recitation preparations to use PER-informed materials, student-centered instructional methods. However, you train TAs and it's up to them, and so the actual use of these or the pedagogies vary among TAs, because TAs also, they're not resistant like faculty, but they've been trained their whole life to do something one way, and now you're teaching them something new, and they try, and some of them do really well, and some of them do medium and fall back on the traditional sometimes, and it's a mixed bag of what the TAs were actually doing, but we were assessing that too. Let me show you some of the results, because this is kind of interesting. This is algebra-based force concept inventory. The top line is the inquiry-based course. The next line is with the real-time physics, which are research-based labs, and with research-based instructional methods in the lecture. Okay, so PERL. Do I have a? Yeah, I do. Okay. So this is the lab, the first one. The next one is the lecture. So PERL is what we call PER lecture, and TL is traditional lecture. RT is for real-time physics, and this is traditional. So here we have the lowest line is traditional lab and traditional lecture, and it's at the bottom. Then we put the real-time physics in, the lecture stayed traditional, it goes up some, okay? So then, this is the reverse. If you keep the traditional lab and put PER-informed lecture in, you also have an increase. And an interesting thing is that putting it in the lecture is a greater effect than putting it just in the labs and recitations. And then if you put it both in labs and recitations or in this inquiry-based course, these two are not significantly different, the data, then you get the highest change. Now, if you know anything about the force concept inventory, 0.3 and above, or between 0.3 and 0.6 actually, is known as the interactive engagement region. And people who teach non-traditionally with an interactive engagement focus usually have courses that have scores between 0.3 and 0.6. Now, back up one more time. This 0.3, 0.6, this is a normalized gain. So what the normalized gain is, it's the post-test minus the pre-test divided by the possible gain, which is 100 minus the pretest, okay? And the reason you report a normalized gain is then you can compare people at Harvard to people at TTU to people at a small community college, because you've normalized it, you've divided it by the possible gain, okay? And so we like to be above 0.3, and these are the two courses where we did it, and they're the ones that use research-based materials to the greatest extent. So it's, yes?
Just to clarify the structure, you had said that the algebra-based and the calculus-based had a 2-hour lab and a 1-hour recitation?
Yes.
Did they also have a lecture?
Yes, yes. They have 3 hours of lecture, I'm sorry.
Okay.
Each class has 3 hours of lecture, and on top of that, they have 2 hours lab and 1 hour recitation. In 2008 was the introduction of recitation for the first time, and that was new for us. And that's a nice place for them to work in a smaller environment, working problems with a TA, to have the TAs help and be where they can ask questions in a smaller environment.
But then there's one version where there's no lecture at all.
That's the inquiry-based course.
Inquiry-based.
Inquiry-based is absolutely no lecture.
Right.
It's all hands-on, and it's the one taught in the room where we meet the PER seminar, and that's the kind of environment that you're working in, yes. And that's no lecture. Okay, so that's algebra-based. Calculus-based. It's like I said, this was where it was hard to get in. We had a lot of faculty who didn't like it, and they were fighting, so we have all these different kinds of labs and coming in. The lowest three, which I think are not significantly different from each other, but are significantly different from everyone else, are where we have traditional lecture and traditional labs. In this case, the Illinois labs did not come out that high in this case. We can talk about why that might be, because I would say they are also PER-based. And then with this combination, a little bit of real-time, a little bit of traditional lab, that didn't do so well. The one time when we had completely real-time physics labs, that is significantly different and higher than the lower three, okay? So now if you go up and you're keeping the PER lecture, so you have research-based in the lecture, then you're higher, independent of what lab you're doing. And again, these are not significantly different from each other. And the only lab by itself with traditional lecture that is in agreement with those is the real-time physics lab. Then these two top lines are honors students, okay? And their honors classes taught by first traditional and then PER lecture, and that's interesting that they're higher. And the first time you look at it, you say, oh, they're higher because they're honor students. But this is a normalized gain, and there's not really a reason that their normalized gain should be higher, okay? Because after you, it should take out that effect. So we have an interesting question and kind of an unsolved open question of what's going on with our honor students because they're getting a much higher gain. The honor students are smaller classes, okay? So it could have to do with the small class setting. It could have to do with it can have to do with the fact that they're honor students, but it made a difference, and we're not exactly sure why. Kevin?
How does the FCI take into account sample size? Like, since that the sample size is 18 and 22, so like does that average out amongst that group? So would you say, since it's a smaller sample size, a lot of them gain higher scores, that kind of skews the data more forward compared to like the group?
It could, and there are probably statistics we can apply to that we haven't done yet. We could go back in and do that. Yeah. We need to look at that because it is an interesting question, and we need to kind of tear that apart.
What's surprising there that RTTL did so well? Because you're not surprised about the Pearl, right? But the second from the top.
This one.
No, the second one there. Yeah, just the real-time traditional lecture. Second from the top.
That's actually a surprise. You would expect that one to be much higher.
That one.
Yeah.
But I mean the second one from the top, which is
This one.
very traditional except for the real-time labs.
It's very interesting. It's the honor students with the real-time labs.
Yeah, they shouldn't have done so well, right?
Well, no, I would like to think
big of a
that
gain?
It's big
What?
of a gain, yeah, right.
it's gain, but I would like to think that the real-time would, the real-time physics labs help.
Yeah.
The
but not
real-time
that
physics
much.
labs are interesting because this is the lab the faculty look at and they say it's too easy. My students don't need this. It's a bunch of garbage. They don't need to look at this. It's really interesting. But then if you look at it, it works. I mean, it's the one that is giving us higher here with these, and it's also giving us higher here.
Yeah, but it's a traditional lab, so it shouldn't have done so well.
No,
TL's traditional
no, this
lecture.
is honors RT
I mean
lab.
traditional
It's
lecture.
traditional lecture.
Traditional lecture, so it shouldn't have done so well.
It doesn't do as well as this one.
Yeah, but it's pretty high.
Yeah, but it doesn't, it's this jump right here, right?
Yeah.
It's that same jump with the honor students between those two.
A different question, could you argue, like, let's say, take the bottom three groups.
Okay.
Could you argue that the FCI doesn't really tell you how much they've learned? It just tells you how they did on the FCI. That these students are still good problem solvers. They understand their physics. They can solve problems from the textbook. They can speak coherently about this, but they just don't do well on the FCI. Could you argue that?
I'm going to say no, but we're going to talk about that
Yeah.
later in the talk. The FCI has a very good correlation to grades practically always.
Yeah.
And it actually predicts things very well, even though it's just assessing concepts.
Yeah.
So you have to say it is just assessing concepts, but it has amazing correlations with other things. So.
Yeah. See, I was one of these bad professors who didn't buy in. I have the TTL. I'm the bottom one. And I'm just trying to say that, yeah, it looks like I did poorly, but my students did well. You know, they learn the material. That's, and I'm wondering to what extent I can
Well,
argue.
let's talk about that after I talk about free response,
Yeah.
which we also
Okay.
have. Okay, I understand that. All right, so let's just do BEMA real quick and we'll get to free response. So this is electricity and magnetism though. BEMA is the force concept inventory for electricity and magnetism. It's a little bit harder. It doesn't have, like we were talking about earlier, groups of problems that all address the same concept. Most problems address different concepts. It probably is considered somewhat harder, and our students don't do as well on it, okay? Now these are algebra-based. There is not a lot of algebra-based data out there that you can compare to. So we kind of don't know where the algebra-based data is. But the calculus-based data is much higher. It's like between 0.4 and 0.6, and people are getting 0.6 and above on BEMA at places like Colorado, where they're putting lots of research-based materials in. So people are getting much, much higher on BEMA than this, and we're very low. A lot of, actually, 0.4, I'd say, most traditional instruction gets 0.4 and below, I would say, on BEMA. And then higher up is non-traditional. So again, though, we have this is with the real time, but the traditional, when we put our own labs in, we got somewhat higher. And then when we put the research-based in both lecture and lab, even in the inquiry-based course, we're not that high in BEMA. We're just not. It's something for us to think about in what we do. So
Those are normalized gains again?
These are normalized gains
The
again.
measuring.
Yes, yes. And I have not in all these slides, but we have lots and lots. You're seeing a small piece of the data that we have. We have a tremendous amount of data, and we have all the post-test data and all the gain data, and not just for these, but for MBT and all these other things that we did. So, and we can present that at some point in time. This is the calculus base, and again, though, it's the same thing. The bottom are the traditional lecture, the bottom three, and I'll talk about this one in a minute. And then we have the non-traditional lecture and the honors, okay? Our honors get up reasonably. It's not totally unreasonable, but it's not great. This class is very interesting right here with traditional lecture. And the difference is this number right here, which I haven't told you about. This is the percent credit given for the labs and recitations together. Okay? So when we first put these labs and recitations in, the faculty said we don't like it, we're going to give it 10% of the grade. Right? Now if you think about it, that's 3 hours of your time. The other 3 hours is in lecture. It's half your in-class time, and it's getting 10% of the grade. Okay? So if you convince instructors, which I was successful at this time, to raise it to 30% of the grade for lecture and recitation together, you can see what happens. That's the only difference between this and these two. It's still a traditional structure. But what happened is that lab recitation was 30% of the grade. You had to pay attention. You had to do something. You couldn't brush it off. And the engineering students, they're good at this. They know what percent of everything is, and they know what they can skip. And there are people that calculate in their head, you know, what do I have to make on the final? What do I have to make on this? What do I have to make on this? This is not relevant. Toss it. I'm not going to do it. Right? And so you can see it. It's right there. There it is. So if you give them more credit, they'll pay attention to the labs and recitations, and you get better results. So that was an interesting piece of data for the calculus-based one. Oh, here I did post-test. BEMA, you usually don't post-gain. BEMA, you usually post, actually the number, what did I just do? Okay, BEMA. I'm sorry, the numbers I told you last time were not true. Let me do it for post. Usually you give post-test in BEMA. In BEMA, most pre-tests are 22-23%. That's it. Which is not a surprise because it's new. It's electricity and magnetism. It's not like the FCI where you have all these concepts like in real life from dropping things or driving a car that you have an experience that you can make some kind of educated guess. It's electricity and magnetism. Most people don't have lots of experience with it. So the fact that the pretest is usually around 22 or 23% is not a surprise. Because of that, most people give the post-test. And what I said last time was not true. The 40, this is the line usually that distinguishes like traditional is here and below, and 40 to 60 is where most of the research based, and now like with Colorado they're getting above 60 in the post-test. Okay, so that's our algebra base. This is our calculus base, and it's the post-test, and the honor students are the only ones that hit that get above the 40. Okay, except for, actually this is good, take that back. Here we are hitting the 40 at least, barely, when we have research-based things in lecture and lab. So we can do that. Okay, so what do we have then? The higher scores on the conceptual inventories are achieved by a combination of research-based labs and IN structure, which is interactive engagement in the lecture. We can get into the interactive engagement region in these plots, particularly in FCI, if we have both PER informed instruction in labs and recitations and lecture. BEAM is not so good. We're not there yet in electricity and magnetism. Now the question comes in is, do we have the whole story, which is partly what you're asking, and that's why we went to pre-response, pre and post testing. And what we did was we gave a pretest in every lab, written pretest where you have to write something out, and then we had a graded post test every other lab. And we tried the best we could to match the post test to one of the pretests, okay? And all of these were designed, the pretest and the post test, to hit on a concept that had been taught probably in lecture, lab, and recitation the previous week. So it was supposed to be relevant. Well, the pretest would have been something they should have seen in lecture the previous week, but had not seen in recitation and lab yet, maybe. But the post test definitely should have been seen in all three by the time they took it. They had to show their work and explain their reasoning. The nice thing about these is that we can move beyond conceptual understanding. We could assess laboratory skills, we could assess mathematical and graphing skills, explanatory ability, higher level thinking skills, okay? So you can do a whole lot of things with pre-response, pre and post testing. We coded them for correctness, which I'll tell you about so we can compare across pedagogies. We also made qualitative observations, mostly on explanatory ability and higher level thinking skills. And this is what we would like to do a whole lot more deeper and in depth and see what we can get out of the same data, looking at it in more detail. And we haven't done that yet. So for correctness, we coded them as completely correct, correct answer, partially correct explanation, correct answer, incorrect explanation, and incorrect. So there were 4 categories. We also did a gain, and what the gain did was that if you had an incorrect explanation, even if you chose the correct answer on the pretest, and then at the post-test you were completely correct, we gave you a gain value of 2. If you were incorrect on the pretest and you moved up to partially correct explanation, you got a gain value of 1. Or if you were partially correct on the pretest and moved to completely correct, you got a gain value of 1, right? We have 2 gain values of 0. And the reason is that if you came in correct on the pretest and you went out correct on the post-test, you have no gain, but you understand the concept. You knew it coming in and you still know it coming out. You didn't lose it. So we separated that out because we think it's important to distinguish these people who understand the concept even though they don't have any gain from people who have no gain. We call this no gain positive, and then this just no gain because these are people who were incorrect to begin with and left incorrect, or you had no change in your status. We also have negative gain. So you can have a correct pretest and you can come out with a partially correct, or you can have partially correct pretest and come out incorrect on the post-test. It doesn't happen a lot, but it happens. And you can even go from completely correct to incorrect. So it happens. All right. So for the physicists, if you want to see the kind of problems that we were giving, this one has 2 parallel plates and it's asking for the magnitude of the electric field at each point. Then we asked them how they would experimentally determine the electric field at point A. This B part is incredibly important because it relates to the lab. They did a lab in 2 dimensions that was very similar to this the week before they took the post-test. And so we were basically asking, did you understand the lab that you did and can you explain it? So that's a really important lab question. And then we have, if the electric field at point A had a magnitude E, the potential difference between points A and B is delta V, and the distance between them D. Which of these is a correct statement, and circle your correct answer. This is kind of understanding what an equation means, okay? And B is incorrect, and it's an equation that they would have memorized, and a lot of them chose them and chose to because it's in the textbook, right? So it means you're aware of the equation, you know it's out there, you probably should use it in this case, but you don't really understand what it means. Okay, so the post-test was very similar, almost identical, except we changed some of the points up here in the A part. Okay, so data. So this is really interesting data too.
Excuse me.
Yes.
Beth Thacker. Were they given the problem as a pretest, and then were they allowed to see it during during the lab itself? Like if for the pretest, this was the example, then they went to lab. Do they have that similar problem in the lab manual that they got to play with, or?
No, the pretest, first of all, just gets turned in and they never see it again.
Okay.
So we keep it. In this case, the lab was essentially a 2D version of what you just saw,
Okay.
but it wasn't pointed out that was the case to them, so that of what they had seen on the pretest.
Okay.
So, no, I guess is the answer. Yes.
So am I correct in assuming that pretest evaluates any prior knowledge that sets a baseline?
Yes, 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 yes. And it could be that the professor in lecture did a good job and that's where your prior knowledge comes from. Okay, so this is our completely traditional. And if you remember, they were very low on the conceptual inventory too. Everywhere you had your TTL, these people way, way, way down here. So probably not the best color coding, but they don't have any completely correct in this. Okay. Oh, this is the game. Sorry, this is the game that I'm doing. Do you remember the game thing? So they do have some game. Sorry, this is some game in there. Okay. So when you put the PER in the lab, you get a little bit higher. You got some no gain positive going on, and you got some partial gain, and you have some gain here. And then when you put it in lecture lab, it's down here. These three calculus-based, first of all, are lower than our two algebra, or three inquiries algebra-based, than the three algebra-based, which is a really interesting thing that we have to think about, and I'll tell you a hypothesis on that. Here's the algebra-based with traditional lecture. As soon as you put PER in lecture and lab, this is good. This is complete gain. This, you knew the answer coming in and going out, right? And here's a partial gain. Well, that's not bad, right? The inquiry is also not bad, okay? I don't know if this surprises people outside of physics, but I'm used to people, only 50% understanding when you do this kind of assessment, so it doesn't faze me. But some people look at this and say it's horrible because they're expecting it up around 70%. But this, I would say that these two are not bad at all. These are our honors, and I'll have to remember why they had a big partial gain here. I think there was an explanation for that. I think there was something that we were coding for that they didn't put in. So I think we can address that. But other than that, they're up here too. Okay. You can see this stuff at the top. You go down, you can go negative. It shows up. Yes.
So you cued me in earlier to the importance of how many points you assign to things as making a big difference in the effects that you get. So were the post-tests equally weighted or equally important in terms of actual points in these various classes?
Yes, and these actually, it was a fair amount of your either recitation. I guess at the time we were doing this, we had the lab and recitation together, and of that total grade, I would say your quizzes at that time were about 40% of that grade. So they were
across. I mean,
across the
to
board,
be a
yes.
purist here, across
Yes.
all of them, it was 40%.
Yes. Yes, they were fairly. There might have been some 35 and some 45 or something, but they were fairly consistent in there as a significant part of your grade to pass the quiz. Now, this one though, I actually want to point out, this is an early quiz, early in the semester, and that actually may make a difference because you weren't aware that this kind of thing was going to happen in a lab or recitation. It's your first time, it hits you in the head, and you're not sure what you want. So that's important when I show you the next one. This is an early quiz, early in the semester.
But you do have T and TL there, so those were the hard-nosed faculty who wouldn't buy into this?
Yes, we had in the calculus-based course, these are also electricity and magnetism problem. They hung on to E&M for 2 years into our grant and would not release it. They had to at one point had to allow this to come in. but they hung on to this traditional
But those
lecture
students
for a
were
long
also
time.
getting the same pre-test, post-test at the same time with 40% allocated to their grade?
That's
what I'm
actually,
saying?
that may not have been the case in this.
In that one?
No, because, no, the difference is it would have as far as the percentage of the recitation and lab grade, but these were the people who gave 10% to that whole part of the grade.
Yeah.
So you'd be talking
So-
about 40% up
so,
10%.
Yeah.
Yeah,
Okay.
yeah. So it's the same percentage of the lab and recitation grade, but these people gave less
So
total
those
percentage to
students
that.
may have marginalized, partially
Yes, and that's-
marginalized these
Exactly.
pre-test, post-test.
Exactly, that's exactly true. And the other thing, our argument for this is, our algebra-based students need an A to go to med school and physical therapy school
Yeah.
and places like that. Our calculus-based students need a C to continue in engineering.
Yeah, so that's kind of a methodological
Yeah.
issue here, right?
Yes.
Because part
Yes.
of your effect there is due to how the points were weighted for the
Mhm.
actual course grade.
Right,
Yeah.
exactly.
Yeah,
And that makes a big difference.
yeah.
Yeah. So let me show you, what is this? Oh, sorry, that was just the A question. And the A gain, and this is the, I can see better here. This is the B gain on the B part. I'm gonna go through these fairly quickly so we can get to some other things. This is the B part of the problem. The A part of the problem, almost always in these is easier, and then the B is somewhat harder, and the C is somewhat harder in most of these. And this is the C part, and you can see that happening there. So then let me just show you one at the end of the semester, okay? These are just loops moving through a region of magnetic field, and you're asked if there's current in any of the three loops, and if there's current, which direction is it flowing, and to rank the currents in the loops, okay? And so by the time you get to ranking, you need some math. You can do the rest of these two by understanding the physics, and in the B part, knowing what we call a right-hand rule about how to figure out the direction in the loop. So this was the pre-test, and this is the post-test, which had a little bit of change, but the same idea. And so I'm going to go fairly quickly, but this is near the end of the semester. I don't have the honors data for this one, and I don't remember why, but I don't have it. But again, we have the calculus base. Now, at the end of the semester, there's some change, right? So maybe you woke up to that this is kind of important, and it is some part of the credit, and maybe you should do some work, but you do better in the calculus-based courses here, and then the algebra-based courses, and the inquiry was really good on this one, and these were also reasonably high by the end of the semester. So those were the pre-tests. So, because I want to flash one more thing up before I get done, I'm going to move on here. Oh, that was the A again. This is the B part, okay? So and again, this problem, the inquiry-based class outdid everyone, but these are reasonable. These came up from the last one. The C part, I think nobody really understood very well. So that's what it is. So what do we have for free response? Well, the nice thing about free response is we can assess things beyond conceptual inventories, right? So we looked at correctness, but we also could ask the question, we could aim it at lab skills, we could aim it at graphing skills, we could aim it at mathematical skills, which we did in parts of these problems, and it's only a piece of the problem. But you can do these things, and you have modeling skills in here, you have thinking skills in there, and we haven't assessed these rigorously yet, but you can go in and look at the data and assess those things. You have their ability to explain, and this is actually an interesting question, because a lot of the calculus-based students, at first, they write short things like a statement for their answer, and they don't really explain, and they don't really give you any detail. And you sit there thinking, well, do they understand it or not? But the bottom line is, they don't either see the need to explain, or we can't distinguish that. But this explanation is something you would like students to have. So we want to try and generate this in our classes, I think, where you can explain your reasoning and your thinking skills. So just because this is, you have a high gain in conceptual inventory, it doesn't mean that you have high performance in other areas. We need to look at this in a lot more detail, I think. Actually, one more comment on my last slide. The other thing is that these are just snapshots. These were post-tests. So this is not like taking one comprehensive assessment. They were just post-tests. On the other hand, I think we got something reasonable out of it. We could find out that our students knew this or knew this, at least at that point in time. And it does give you significant information as far as instructors. Okay, so there's one last thing. I'm kind of interested to see what you guys say, and it's going to go fairly fast because I'm going to run out of time here. But on a lot of these problems, we had a lot of students who could choose the correct answer and not correctly explain it. And this happened a lot, more than we would have liked. So we decided to kind of do a sub-study on this. And so what we did was we gave the same question in multiple formats, okay? And what we gave a multiple choice only, we gave a multiple choice and explain only, ranking, and then we gave some other formats because we were running out of things to do, and we said, well, let's just try and change something about the problem and see what happens. The students in the large classes then were randomly given one of the quiz formats, all right? We just put them on different colored sheets of paper, and they randomly got different formats. We did it with 2 different questions, and we did the first one in 6 formats and the second one in 3 different formats. So here's the first one. This is the stem of the problem, so everyone had this part of the problem. You know, imagine that you are comparing 3 different ways of having a ball move down through the same height as in the picture below. There, 3 cases are dropping, sliding down the ramp, and swinging, okay? And then, if you had multiple...
What was their friction?
It wasn't, or actually, it's probably bad that it didn't say that. That's why you want to explain in something like that. So, this is the way it was run. This was taken from the University of Illinois, actually, from one of their problems. And it, oh, this says no friction on the ramp, sorry.
Well, what about air friction?
That's what's not said. So the air friction is not mentioned, and this is no friction on the ramp, okay? So if you're multiple choice, you just get multiple choices, okay? So the 2 questions then are, in which case does the ball reach the bottom with the highest speed? And your options are the 3 things, dropping, sliding, swinging, or all the same, okay? And in which case does the ball get to the bottom first, was your other question. And you also had those 3 and all the same. This is pure multiple choice, boom. Right? Okay, now if you had an explain, you had the same 2 questions, but it just said explain your reasoning. Okay? So you're supposed to answer the question and explain. Or you could have had a, this is both. You choose the correct answer and explain. So this is multiple choice plus explain your reasoning. So you're given a set of answers, but you still have to explain your answer. We also had a ranking. And actually, you could not rank 2 of the cases, and so nobody actually got that right, so I really don't want to worry about this one. And then we had 2 other formats in there that I'm not going to tell you about, so I'm going to focus on these 3 because they're the more important ones. This is pure multiple choice, okay? So you can get, you know, 55 to 70% correct when you just give that problem as pure multiple choice, all right? As soon as you have to explain anything, even if you're given choices, you have this big correct choice, incorrect explanation. It's giant, right? Those green bars, okay? And even in these other formats. And your completely correct drops dramatically, boom. It completely drops. So we have a lot of this going on, so we need to think about what this means, you know, as far as multiple choice free response. And it's just a single problem, and I know that, but...
Obviously, it means you should never ask students to explain, because if you don't ask them to explain, they get it right.
They get it right.
70% of the time.
Exactly. Exactly. That was calculus-based, this is algebra-based, it's the same thing, right? So, multiple choice, have to explain in any of the other cases. Yeah, so it's really interesting. This was our second problem. Actually, I'm going to skip through that since we're running out of time and come to some conclusion. It had the same kind of thing, though, in the second problem. But the second problem had ranking, and these bars went down significantly when we had ranking, multiple choices. So let me finish up and then we can come back to that if you want, but the ranking problems change. Now, both of these, well, let me show you this problem over here. This one was, these are all frictionless surface and all the masses start from rest. And what you want to do is rank from greatest to least the final velocity, okay? And then you rank from greatest to least the time it takes to get down the ramp. But you had multiple choices. You had lots of choices in here, okay? And what that did was it brought down this correct choice, incorrect. It came down a whole lot. Well, these two are the more important pieces. It just brought it down. So anyway, let's summarize this some. What do we learn from conceptual inventories? Well, when you use P&R form materials, in just the labs and recitations, you see an increase. When you use it just in the lecture, you see an even greater increase than just in the labs and recitations. And if you use it in the labs, recitations, and lecture, the increase is greatest. I mean, that was our takeaway. We don't have stellar data like the highest off-scale FCI data, but you can see it increase as you put these methods in. And it's pretty dramatic and it's important. So what are the pros and cons of these conceptual inventories? They're vetted, they're valid, they're reliable, they've been tested for validity and reliability. You can compare them across institutions and across classes, and they're stable, and that's wonderful. And they're multiple choice, so you just send them off to a machine to grade. Not a problem, right? So it's easy. Cons, they're not comprehensive. The FCI is nowhere near a comprehensive test of your course, and that's actually troubling to some of us because they're about the only thing out there and people are starting to use it for that. And I get very bothered by that because just because you do well in the FCI doesn't tell me about a lot of things, and I don't like it to be used that way. So they're limited to assessment of conceptual understanding, and that's it. That's all you're assessing. We could probably list more pros and cons, but they don't necessarily then tell the whole story of conceptual inventories. So we did the locally written free response pre and post test. They're fairly powerful. They're useful to find out what's going on with your students. They yield information beyond conceptual inventories on students' skills and abilities, thinking skills, and lab skills and math skills. And it's a very interesting tool, even though it's just a snapshot. It's very important. We found that the large classes, you increase PER. We saw this same thing. The more PER you put in, the better they did on the free response pre and post test, consistently. And the increased students were not on every problem, but they were usually at or above the other classes, and their PER informed also. So there's a good thing there. They also have pros and cons. So what you get from them is you can assess a whole lot of other skills beyond concepts. You can assess problem solving, thinking skills, lab skills, math skills. You can design problems to assess whatever skill you want to assess. They're not comprehensive. They're snapshots, and they're useful like locally for your own department and less useful for comparison. However, some of us would like to develop this. They're not yet used for comparison. Some of us would like to develop a database of free response problems that people can use nationally and draw from and compare. You'd have to have a rubric to grade it, and people would have to grade by the rubric, but you could still compare across institutions and across that, and we'd like to try and get that started. And they need to, if we're going to do something like that, they need to be tested for validity and reliability, which seems my point, so we need to do that. So that's part of our further research and development. We want to look more into the use of free response in assessing particularly explanatory skills and thinking skills. And we want to think about, can we get together a database of vetted, valid, reliable, free response questions that you can compare across universities, across classes. And we've actually tried one grant with this so far and failed, but we may try some more and see if we can get it through and see if we can get that going. So that's one more thing for this group. These problems, the dropping and all, we are having trouble publishing this. And we're trying to figure out why and how we can get it published, because we think there's something there and we have some good things to say. And so if anybody wants to look at that, we'll send you what we've put out, because we've tried it a couple of different places. And if people think we're trying to destroy multiple choice, they get really angry and they're not gonna give it good reviews, is what we're finding. So you have to figure out how to write it. So we're gonna look into that. But I'll stop there because we're out of time. Thank you. Okay. Questions?
So you said that, was it the BEMA that we don't do as well on?
We don't do as well.
Is it just the gains that we don't see that are where we would like them to be, or is it actual
The post is
performance?
also not as high
Okay.
as we'd like it to be.
How does the pre compare to other institutions? Like, are we coming in lower and just not gaining? Like, it's conceivable that you could come in so weak that it's hard for you to.
No, it's actually similar.
Okay.
It's actually similar in
Interesting.
that one. Yeah.
Okay.
Yeah. So we're actually not, yeah, we're not getting that high on post or gain. Yeah.
Can you explain once again what's the difference between a traditional lab and or I saw you have a traditional lab there and I think you said it was a PER or an interactive lab, and then there was a PER lab.
We've had traditional labs were the ones that at Tech have been there for like 30 years. And there's a certain format and you do a traditional lab write-up after the lab. And let me see how to describe it, because it's a very distinct format and it's a very telling. I mean, this is what we're going to do. They tell you what they're going to do, and then you tell you what to do, and then you do it, and then you write down your data, and then you take it home and you write up a traditional lab report. And that's the kind of extent of it. The rest of them are research-based. Now, we used a couple different kinds. We've developed, what we're doing now is essentially research-based developed here. But in this process of getting there, the real-time physics labs are research-based labs developed and published by someone somewhere else. Okay? The Illinois labs were developed at the University of Illinois, published and used here. And so there were different kinds of what I would call research-based labs that we tried and put in. But they all have a different kind of flow and focus. Yes?
So, I had a question as it relates to the research-based labs. Does that mean that you're trying to work with a variable and is that more? I guess I don't understand the difference between, because you're using this traditional and research-based. Is there a reason why you use the term research-based?
The research-based labs, they vary, but one of the things is a lot of the research is on conceptual understanding, which is why you have the FCI and all these inventories popping up. And people who have developed research-based labs, they try and put conceptual understanding in. In a laboratory situation, it's an understanding of the physics of the lab, which is not often done. I mean, in traditional labs, it's
So
more
it's
do
not a
this, do this, do
recipe.
this, write the numbers down and take it home. And here it's, okay, why would you do this? What would happen if you raised this track higher? What would happen? And during the lab, you're asked questions about, so what if the track were higher? What if it were lower? Make predictions.
Right.
And a lot of the times you have a prediction, usually you have a prediction within the lab. Okay, so we're going to do this, predict what's going to happen. I mean, you know some physics, predict what's going to happen. And they write it down in their lab notebook, which gets turned in, but you don't grade predictions because it's a prediction. It can't be wrong. It's what you think is going to happen, right? And then you do the experiment, and then you see what happens, and then you go back and try and match up your physics to it. So you do this as you go through the lab. So it's a different kind of focus on the lab because you're also trying to get at the physics concepts of what you're learning. And in that sense, it also irritates a lot of traditional faculty because you're not focusing on the data and the statistics and that part of it. You're also bringing in all this conceptual understanding. So it's a different focus. And we have to think about how we focus labs. And the AAPT has just recently put out new guidelines for labs because it's a real question. What should a lab be? How should it be focused? What should you be learning from
So
labs?
it sounds to me like it's more of a scientific method-based approach as opposed to a directional recipe-based approach.
I could, and coarsely, yes.
When you call it research-based, you mean that the labs have been developed based on research and determining what the best practices for?
No, research
that?
on students' understanding of concepts.
But the research has been, it's not that you're claiming that the students themselves are in some way doing research in the lab.
Oh, no.
Right,
It's,
okay.
it has to do with people have interviewed students or observed them in classes and they understand why they're struggling.
So
and-
it's
and
the research informed the design of the lab.
Okay.
Yes.
Okay, thank you. I guess
Yes,
that's-
it's the conceptual understanding of the students that has been researched. And there's published data on that. And when you design the lab, you know what they're probably going to think. And so you ask them the question that they're probably going to think so that they get it wrong. And then it triggers their head. So they have to redesign their brain and get it right.
Gotcha.
So, yeah.